So during the last lecture, we derived this expression. We proved in fact that entropy is a property and change in entropy can be obtained by integrating dq by t over a reversible path, right? A process has to be reversible. So it is integration from A to B that will give you change in entropy, which means SB minus SA. S is a term letter which we use for entropy. So SB minus SA, that means entropy at point B minus entropy at point A, entropy is property. Now you can also immediately pay attention to the unit of entropy. If SB minus SA, that is dq by T, Q is for heat, that is it will be joules or kilojoules, and T is temperature but in Kelvin. Always remember this. When you come across entropy, dq by T, T is always in Kelvin. So unit of entropy, you can say it is either joules per Kelvin or kilojoules per Kelvin. And if we are talking about specific entropy, that means entropy of 1 kg of any substance, then it will be joules per kg Kelvin or kilojoules per kg Kelvin. Okay, so this is something which we did during the last video, except the units which I have introduced now. Now let's go further, and I want to pose a question here. I want you to think and then pause the video after I pose this question, and then go ahead again, play the video. This expression tells you that if you want to find out entropy, the process has to be reversible, and only then you can do the integration. That means if you have a process, you know how the process takes place, and then you can do the integration and find out change in entropy, but the process has to be reversible. But you also know that in nature, in reality, the process is always irreversible. There is no reversible process. So if you imagine gas expanding, initial state, final state, the gas expands in a cylinder or anything, anywhere, if it expands, the process will be a real one. But there will be entropy change, and how will you find out entropy change? If you had the relationship between the process occurred, you could do the integration, but this process is irreversible. But the expression which we have is for reversible process. So how can we use this expression for finding out change in entropy? Okay, so this is the question which I am going to address now. So you can, if you want, you can just pause the video, think for a few minutes, and then join back. Okay, welcome back. So what I am going to do now is I am going to draw a TS plane. So this is temperature, entropy, because entropy is property. So instead of PV plane, now I am drawing TS plane. Along x-axis is entropy. Okay, so let's say that this is one state, this is another state of a system, and let's say that the system undergoes property changes, a process occurs, system moves from state 1 to state 2. And this is a real process. It's a real expansion. Obviously, when you have real process, then you will have an approximate path, and that will be shown by dotted line. I have explained to you this. Only a reversible path process can be represented by a continuous curve. This is a dotted thing because it's a real process. Okay. And if you want to find out change in entropy, how will you do that? How can you find out change in entropy? When you have this path shown by dotted line, because it's a real thing, real process. But now see, because you are interested in change, that means change in that entropy when the system reaches to from 1. Okay, so it is, and you know that it's a property, and change, it doesn't depend upon the path. You can take this path, another path. Similarly, one can imagine a reversible path. Okay, one can imagine a reversible path. So actual path is irreversible, but you can imagine a reversible path, and over this path, if you find out dq by t, again you can have this integration over this path, which is a reversible path. If you find out, do the integration over reversible path, whatever answer you find will be same for this, for irreversible, because ultimately the system is moving from state 1 to state 2. So it doesn't matter whether process is reversible or not, but actually process is never going to be reversible. So you can, my point is this, you can apply this expression to find out entropy change even for real processes, because entropy is a property, it's a state function, it doesn't depend upon path. You can imagine a reversible process, and over that reversible process you can do the integration and you can get the expression. Now all that is, this is little abstract. When we take the numericals, this thing will be clear. But I would like you to remember this. This is an interesting point. It's a property. So path doesn't matter. Imagine a reversible process connecting the two states and do the integration, find out the change in entropy. That would be same for this process. Thank you.